right, so today we will be going a little bit over integrative simulation of compression molding and pre-preg overmolding. All right, a quick outline of what will be discussed in this presentation, this webinar that you guys are attending. Basically, a quick introduction to composite materials, the different composite materials, some case studies that we've done with other our partners with different types of processes, like your compression, your overmolding, RTM, and then we'll go through just a quick conclusion. Okay. So types of composite materials, typically there are two types, your discontinuous and your continuous type. The discontinuous is used in your thermoplastics, like your injection molding process, or even compression molding of thermoplastics. We have your GMT, LFTs for your thermoplastics, your thermosets for your SMCs and DMCs. Your continuous type, which is kind of like a pre-preg or a matte or a preform, which consists of like your 3D fabrics and different unidirectional fabrics for your pre-pregs or your preforms. All right. So for discontinuous types of composites, we have your randomly oriented, like fibers, and we have your discontinuous and aligned fibers. Doesn't necessarily have to be fibers, but I think fiber is an easy way to visualize. Continuous types, we have our, again, aligned and also, as mentioned, like a fabric, your pre-preg. So some images of what the different types of material are. Again, your thermoplastics, you have your GMT, your LFT, and your LFTD, direct long fiber thermoplastic. For our thermoset, we have our sheet molding compound and our bulk molding compound, DMC. Different types of manufacturing process for these different types of composite materials include, but are not limited to injection molding, which typically consists of fibers, short fibers, top fibers, compression molding, which consists of your SMC, GMTs, injection molding, injection compression molding, and overmolding, and your RTM type process. So compression molding of SMC materials. In the compression molding of SMCs, you basically start off with a solid, like a preform or a charge. Place it in the mold, and then it can, if it's draping, if it's pliable to drape, then the material will start to drape in the solid, and with the heat and the compression, it would start to turn from solid to a liquid phase. During the liquid phase, it's compressed to create a final shape, and then solidifies to your final part, and then it's ejected. So integration of two simulation software packages. This one we're going to briefly discuss using LS Dyna for the draping. So using LS Dyna, we have the ability, or there is the ability to consider the elastic type properties in the solid stage of the charge during the compression molding. So before the material is fully compressed and it's in what we call flow. So from LS Dyna, the material cards with non-isothermal properties is brought into simulation software, flow simulation software, Moldex 3D. Then Moldex 3D, those initial conditions will then be read in Moldex 3D to calculate the final compression, which turns the material into kind of like a liquid flow stage. Using simulation to calculate this flow stage, we can export or get information from the final shape, final part, such as your fiber orientation. So we have a unique model to export or get the fiber orientation to export out for further structural analysis. Not only is it for fiber orientation, we can export out like weld lines and such that can affect your mechanical properties. All right, so here's just a quick animation of what is done in Dyna. So we're compressing the charge. So once it gets to its final shape, before it again starts to flow, the temperatures and the pre-shape, the drape form is brought into Moldex. All right, so this is, we can see in gray, the charge when it's being compressed still in the solid phase, kind of like the draping. And then we have our final part in the yellow. On the right, we can see the temperatures during that compression. So that'll be our initial boundary condition of the charge prior to Moldex 3D calculating the flow. All right, and here's just an animation of the flow or the charge being compressed and material flowing to complete the fill of the part. Because we have a big jump at the end there, here's just a quick snapshot of the flow at different time steps. So the first one, top left, the initial charge input from Dyna, what the shape is. And then at 1.05 seconds, progression at 4.2 seconds, and your final part once the compression stage is complete. So again, from simulation, from Moldex 3D, once we have the, we've done the flow calculation, we can export out displacement. We can see the different displacements in the part, how the part is either warping or shrinking or distorting at any region of the part. Fiber orientation. We can use this to analyze how our fibers are oriented in any direction that is important to the strength of the part itself. So if you can determine whether the fiber is aligned the way a user is expecting or wants it to help with mechanical properties, with the strength of a material or the part. All right, so we can show you the initial fiber orientation. This is a cross section, by the way, of the part. Then we can now show you how the fibers are oriented after the compression stage. So similar to the previous slide, But here we can look at different cross sections, cut through different sections of the part, and look at in the fiber tensors itself. Okay. So charge thickness and charge placement for compression molding is important, and running simulation can help to identify how the volume of the charge being the same, but if the height differed or if it's placed in different regions of the mold, how will it change fiber orientation? How will it change endofill regions? How will it create or resolve defects? Can be seen if modeled in simulation. Okay, so for example, top left, we have a 4 millimeter charge in thickness. Again, the overall volume of the charge is the same. It's just the thickness that's changing. We can see that the fill pattern is different from the 8 millimeter charge and the 6 millimeter charge, with the 6 millimeter charge at 70%, giving us or resulting in the most equal flow progression through the part during the compression stage. Right? So again, let's look at fiber orientation with the different thickness in the charge. As you can see, depending on where the fiber alignment is important for the part's strength or mechanical properties, the charge thickness in itself, due to the difference in flow, will have an effect on how your fibers are being aligned. So anything you see in red here is highly oriented in the X direction. Anything close to the blue means it's not aligned in the X direction. It's random. So the closer it is to blue, it's random. The closer it is to red, the higher it is being the fiber is oriented in the X direction. Okay, so we can see the 8 and the 6 millimeter charge have high fiber orientation in our X direction. So the closed loop system or solution, start off with LF Dyna to get the drape form and the initial temperature conditions. During the draping and initial compression, bring that preform charge via LF Dyna and the initial temperatures to Moldex 3D to calculate the flow to give you fiber orientation, potential knit lines, potential defects. Export the information from Moldex into Digimat RP to set all the micromechanical anisotropic properties and map it onto a model, map it onto the model to be exported back into, here it says LF Dyna, but any major CA or FEA software, ANSYS, Abacus, to do its final structural analysis on the part. So this will give you more realistic anisotropic properties so that when you do the FEA analysis, it will be better or more correct than an isotropic part. All right, so that was compression molding. Now let's go over composite overmolding. Again, basically, with LF Dyna, we're going to be overmolding, creating a preform fabric, and then overmolding with the plastic, thermoset or thermoplastic. All right, so same thing as the compression molding. Have our draping analysis. Once we have the draped analysis of the fabric, we can model in the charge in Moldex 3D and use that to finish the flow calculation to determine what's happening with the fabric, your shears, fiber orientations, and such. Okay, so here is that same project. Bottom right, we can see the animation, a slight animation of the flow as the material progresses through the fabric. All right. With simulation, we can get modulus of our final part once the plastic or the material has been overmolded or integrated into our fabric. So we have our X modulus, Y modulus, and our Z modulus. So the X and the Y is within about 40,000 MPa. And our Z modulus, for the most part, is near 0. All right? So warpage behavior with that overmolding, we can predict how the part will distort after the plastic has been compressed. So quick case study. Here we have overmolded parts. The blue, as you can see on the bottom left, it will be modeled as your an isotropic steel and one with the fiber in certain direction, laid in certain direction. To the right, we can see the part in yellow, and in purple, we can see the feed point, the cold runner. Kim, I will answer your question in a second. Please give me a second. So effective material properties, as you can see, using the different fibers, the orientation of fiber, the mat being laid, depending on the orientation of how we lay the fibers, we can get very similar strength between steel and a UDS glass epoxy type material, like the fiber. All right, and depending on how the fiber is laid down in the initial stage, can affect results such as your warpage. So this one, we're looking at the Z direction. So the 010 means the fiber is laid directly in the Y direction. So in this direction, the fiber is going in that direction, okay? Towards the Y, follow the arrow. The middle image, we have a fiber that's kind of not woven, but laid perpendicular to each other in the X and Y direction. And we can see how that affects the part warpage. In the Z direction, same thing for just laying the mat or the fiber in just the X direction. So the placement or for example, if you have a woven mat, how those fibers are woven together or laid down will affect part strength, displacement, and that kind of stuff. So that can be visualized through simulation, calculated and visualized through simulation. All right, the last one for this presentation, we're going to look through RTM, resin transfer molding. So resin transfer molding is very similar to the two processes that we've shown. If you're not familiar with it, basically resin is pushed or flown through like a fiber mat, like a fiberglass mat or something, and cures. So the different types of process, RTM, vacuum assisted RTM, RFI, ERTM, okay? Again, very similar process and can be visualized with LF Dyna or simulation. The draping process, we can determine how the fibers or the ply ends up being during the draping process prior to injecting resin. Okay. Moldx 3D or simulation supports shear effect on the mat itself, okay? We can see that there is difference with shear, with taking shear into effect and not taking shear into effect. So a quick case study of a very large vacuum assisted resin transfer molding part. We are focused mainly on the one in red, site 2. All right. So for this particular geometry, we had about 3 million mesh elements. We ran 2 different scenarios with the number of feed points or melt entrance for resin to flow through. Simulation results compared to actual results. So for the top 3 images, focus on where the red line are. So the red line is indicating flow front progression of the resin as it's injected into the mat. Because this is a very large part, it's a little bit difficult to see, but as we can correlate, it does match pretty well with the flow front progression of the resin during this RTM, vacuum assisted RTM process. Here's just a quick animation showing different number of inlets. So 2 different scenarios, one having 4 inlets or 4 feed points for the resin, which is on the left, and on the right showing 7 inlets. So 7 feed points to this model. So what the graph is telling us is just kind of showing us the opening and closing of the feed of the material onto the mat. All right. So from simulation, we can take a look at the viscosity. We can see viscosity results and your conversion rate either at end of fill or during the process of the resin flowing through our mat. So we have our conversion and viscosity for both the 7 inlet, which is on the bottom, and our 4 inlet control, which is on top, okay? So as we can see, let me see the next one. Yeah. Next one, this slide is conversion The scale is not exactly the same, but with the 7 inlets, we can see that the conversion rate at the end of fill, so when the part is completely filled, the conversion rate is a lot lower, which means the material has yet to cure. Not yet to cure, but it'll result in more equal cure time from one region to the other. The one on the left, as we can see in the middle, because there's only 4 inlets, the conversion in the middle happens fairly quickly compared to the last or nearing the end of fill. So in the middle, we are already at 40% conversion. So the material is already cured 40%, while at the end, the conversion rate is at 0. So it hasn't hardened yet, basically. While the middle is already starting 40% hardened. All right, so quick summary. With the latest advancements in simulation, both the draping, flow solver, the manufacturing process using these different types of fibers and such can be simulated accurately. With the closed loop integrated workflow available, we are able to accurately predict and get much more accurate prediction of FTA due to material behavior and part performance.